Hi everyone, welcome to the our new YouTube channel, The House of Chemistry. So today's topic is Radical Chemistry Part 2. In this topic, there are four subparts. First one is frontier orbital interpretation. Second one, examples on radical nature. Third one, Captodative effect and its example. Fourth one is stability factor. So in the first one, frontier molecular orbital diagram FMO. Question is why we need FMO in radical chemistry. So to understand this one, we will go to first carbocation, second one carbanion, and then methyl radical. So consider this molecule as a methyl cation. So we can say that methyl cation, due to deficient of electron, this is electrophilic in nature. While suppose this molecule as a methyl anion, so due to two extra electrons in the p orbital called as nucleophilic. While in the case of methyl radical, this is a mid of carbocation and carbanion. So to interpret the nucleophilic or electrophilic character of radical to be understood in the term of FMO description of substituent effect on radicals. So this is the energy level diagram of methyl radical. In this, these are three CH bonds, one CH bond, two CH bond, three CH bond. So these three sigma bonds, and these three sigma bonds make six electrons. 1, 2, 3. 3 sigma CH bonds. These are doubly occupied. Why doubly occupied? Due to one covalent bond require minimum 2 electrons. So 6 electrons are there. So this is one electron makes a different orbital called singly occupied p orbital named as SOMO. It has a higher energy, and when this is bonding orbital, so similarly here is anti-bonding orbital sigma star CH orbitals. So this is the energy level diagram for methyl radical. We are considering SOMO interaction with HOMO-LUMO interaction of the pi bond. So we want to know that whether this radical act as a electrophile or nucleophilic. So now taking this reaction is an example of addition to a pi bond. This radical adds to this pi bond, makes this new radical. So in this first part, we are dividing it into three parts. First one is unsubstituted system, this one. Second one, R radical is an electron donating, Z is electron withdrawing. While third one is R electron withdrawing, Z is electron donating. So in unsubstituted case, we know that SOMO and LUMO, SOMO and HOMO have equal energy difference. So we cannot predict easily that this radical, R radical, act as a nucleophile or electrophile. While in the case of when Z is electro-withdrawing, so Z electro-withdrawing makes this alkene unstable. So HOMO and LUMO will shift at a higher energy level. So HOMO shift at a higher energy. Similarly, LUMO shift at a higher energy. While R radical as electron donating makes this radical as a stable. So SOMO will stabilize by lowering down the energy. So the interaction of this SOMO electron with LUMO makes this R radical as a nucleophilic. While in the case of R is electron withdrawing group. So R electron withdrawing means it is unstable radical. So unstable means shift to higher energy. While in case of Z is electron donating. So electron donating group means it will stabilizes the alkene. So stabilize means lowering down the energy. So here, so these are the two examples that we can understand that concept easily. So in this first reaction, we want to know that whether this radical is an electrophilic or nucleophilic. You can see here, this reaction is a addition to a pi bond reaction. Okay, so this radical connects to 1 and 2 electron withdrawing groups, and this alkene connected to this electron donating group. When R group act as a electron withdrawing and alkene as a electron donating. You can see here this example. R as electrovitring and Z as a electron donating. So makes this radical as an electrophilic nature. So this electromalonate radical act as a electrophilic. Similarly, the reaction 2. This reaction, methyl radical abstracting this proton while chlorine radical abstracting this proton. Why? Because chlorine radical higher electronegative than the carbon, this carbon atom. So this is an stable radical. So this is unstable as compared to this Cl radical. So this Cl radical abstract this proton because of lowering down the energy of SOMO. Okay, and here this electron, this radical, this unpaired electron or radical abstract this proton by increasing the energy. So it will abstract this proton. Similarly, you can see here methyl radical is nucleophilic with high energy SOMO. The chlorine is electrophilic, it has low energy SOMO because it is electronegative element. Attacks CH bond of the terminal methyl group because they have highest energy HOMO. Captodative effect. Radicals are stabilized by an electron withdrawing and an electron donating group at the same time. This radical stabilized by two groups connected. One is electron donating, electron withdrawing, electron donating. So these are the examples. Propiononitrile radical. This radical connected to one side electron donating, electron withdrawing. Similarly, this radical connected to OH as electron donating and carboxylic acid act as a electron withdrawing. So these radicals are highly stable. So what is the here in the stability factor? These are the four parameters. This is the decreasing order of the stability. First parameter is captodative effect, second resonance effect, third one hyperconjugation, fourth one steric effect. So problem 1 arises here, which radicals are persistent and which are reactive. So these are the 5 examples, 1, 2, 3, 4, 5. In this, some of the molecules you can see here are sterically crowding, this one and this one, and some of them are not sterically crowding like 1 and 3. So 1 and 3 are not sterically crowding. So these are the reactive molecule sterically crowded by these 4 methyl groups, these O radicals. Similarly here this O radical sterically crowded by this one tertiary butyl and this one tertiary butyl group. Similarly this radical sterically crowded by 3 phenyl groups. So molecular number 2, 4 and 5 are persistent due to steric crowding. And this radical is stable due to resonance in nature. So in the next problem, arrange the following molecule in decreasing order of radical stability. So this radical stability 1, 2, 3, 4, 5, 6, 7, 8. These 8 molecules are there. This first molecule is primary radical, or we can say that it allyl radical. This radical is stabilized by resonance. This radical stabilized by hyperconjugation. This radical stabilized by what? Which factor? This radical stabilized by hyperconjugation. This radical also stabilized by hyperconjugation. These 3 molecules are unstable. This molecule is stabilized by resonance. So in the stability parameters, resonance came first, then hyperconjugation. So first and 8 have higher stability than 2, 3 and 4. So similarly 5, 6, 7 are unstable because when hydrogen atom is there, so it is difficult to remove the hydrogen atom to achieve this radical and this radical because it requires a lot of energy. Thanks. I hope you like this video.